Den lyser här. Okay. The topic for today are regular expressions, finite automata, and context-free grammars. What do you know about these concepts? Familiar? Regular expressions. What have you used regular expressions for? Search for something? Yeah. Most programming language has support for regular expressions. You can define your own regular expression and search for certain patterns in a string, basically. That's what they are most commonly used for. Finite automata is actually closely related to regular expression. It's a way for, well, how to implement this search part for regular expression. And context-free grammars is something similar to regular expression in a way that they are defining a language. But let's move on. Defining a programming language. How would you define a programming language like Java? If I asked you, would you define Java? How would you start? It must include all possible correct Java programs, an infinite number of them. It must exclude all non-correct Java programs, also an infinite number. You should specify what is a Java program. How would you proceed? Well, you might take a top-down approach and say a program consists of one or more classes. A class starts with public class ID, followed by a set of member definitions. A method starts by like this. This would be one way to describe what a Java program is. And tiny details, what do we mean by an identifier and a number? We could use another part of our definition saying that an identifier consists of letter, digits, and underscore, but they must start with a letter or underscore. An integer is either positive or zero. This one could be one way to specify the language. Do you agree? Something like this. If you take a look at the Java specification, you will see something that looks like this. They are specifying the syntax of Java using something called context-free grammars. This one should be read as a program consists of one or more class declarations. A class declaration contains the keywords public class ID, left bracket, and then we have any number of field and method declarations. A method declaration consists of these statements. We have a number of different statements, and each statement we could describe in this way. If you take a look at the Java specification in appendix somewhere in the back of it, they have 5 pages describing Java in this way. And also, they have another part describing details. What do we mean by an identifier? What do we mean by an integer? What do we mean by a double or things like this? And then they are using regular expressions. A letter is something that looks like this, a digit like this, and then in the Pascal language, an identifier was described as it must start with a letter and then any combination of letter and digits like this. So there are 2 parts in a language definition in a programming language. This is the syntactical structure, and this is the smaller parts that are the building blocks used up in this one. So we're going to talk about this type of language definitions, but before we start, what is a language? You have been programming for the last 3 years, but you must know what a language is. Well, a language in computer science is a rather technical concept. A formal language is defined of something called symbols, alphabet, and strings. Symbols, the smallest units. Alphabet, a finite non-empty set of symbols. These are all the symbols we are using. A string is a sequence of symbols from the alphabet. It's just 3 words and they are not very complicated. A, B, B, A, B, 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 A. They are strings over the alphabet A, B containing the symbols A and B. So symbols are the building blocks, the alphabet are the set of all available symbols, and strings are just sequences of the symbols from the alphabet. A binary number is a string over the alphabet 0, 1 with symbols 0 and 1. So these are 3 concepts that we are using when we are talking about formal languages, alphabet and symbols. Other concepts, the length of a string, denoted like this, is the number of symbols in the string. So for example, if our string was ABBA, the length of this one would be 4. We have a special symbol called the empty string. It is the only string that has the length 0. Closure of an alphabet. It is all the strings you can form based on these symbols. So if I have the alphabet A and B, the closure of A is whatever combination of A and B you can form out of this one. An infinite set of strings. Yeah? And then a formal language over a given alphabet is any well-defined subset of the closure. You have the set of all strings, and you say that, but only these particular strings are my language. They are a subset of all of them. So if we go back, what would be the symbols in this one? What are the basic building blocks of a Java program? Well, we have keywords, public class. We have identifiers defined in different ways. We have parentheses and brackets and things like this. This is our symbols. You can form an infinite number of different programs using these symbols. Some of them are correct, others are not. Did you get this idea? We have smallest possible constructs. We can form sequences of these smallest constructs. Some of them will be a Java program and some of them will not be a Java program. So the Java programs are a subset of all possible strings. Some of them are correct and the other strings, most strings are not correct. We are talking about definition. How do we define a language over some alphabet? They are often infinite sets. That means we cannot list all the correct programs. It will be impossible to have a list containing all valid Java programs. Too many of them. Recognition. Verify that a given S belongs to a certain language. We have something that looks like a program, but we should verify that this one is the correct program. It's the recognition problem. Verify that it is correct. Parsing. We are recognizing that it is correct, or we are also building some kind of internal structure. Do you know what a DOM tree is for XML? You have your XML file and you are reading it and you're constructing a tree inside. This is parsing. First thing that happens is that they are checking that your input XML is correct. They are doing it in some clever way. And then they are building up an internal representation of the program. This is parsing. We are doing recognition to see if it's correct, and then we are building up some language structure of it. When you are parsing something, this is what you do. The simplest type of languages are the regular languages. Each regular expression defines a language. If you have been using regular expression, you have used a question mark and plus and different constructs. But in the purest format, you only need 3 different operators. All the other ones are syntactic sugar, actually. So a regular expression is a pattern consisting of the selection operator, A or B, the concatenation, A followed by B, and A star, 0 or more A's. You're familiar with this, guys? Operator priority. This one has the highest priority. Concat has the second highest, and this one has the lowest. So this ugly regular expression should be interpreted like this. Star is attached to B, not to A and B, for example. Yeah. Every string that matches a pattern, a regular expression, is a part of the language. So if I have a regular expression like this, then there are only a few strings containing A and B that match this one. And they are our language. They are a subset of all possible strings containing A and B. So each regular expression defines a language. Those that are recognized by the regular expression, it's our language. So each regular expression defines a new language. So assume that we have an alphabet sigma. Assume that we have a regular expression using sigma. Then each such regular expression defines a language. That means those that match this regular expression, they are a subset of the closure, and they are our actual definition of it. Oops. As you can see, it will be rather formal. Simple examples. Assume an alphabet. We are only using A and B. I will use A and B a lot this lecture. Then this regular expression, AB followed by empty string, BA or AB. It defines a finite language. These are the only strings that match this regular expression. So regular expression here defines this language. Do you agree that these are the only ones fulfilling this regular expression? It says it should start with A and B, and then it should be empty string, BA or AB. It's only these that are possible. B followed by A star, it defines an infinite language. It must start with B and then any number of A. These are all the strings that match. It's an infinite number of them. AABB defines the infinite language, any combination of AA and BB. Yes? Okay. Exercise. Consider the alphabet A and B. Write a regular expression using A and B that recognizes all strings that has the length of them are an even number. Any combination of A and B that has an even number of symbols. Could you write down a regular expression recognizing these strings? Didn't you tell me that you've been working with regular expressions? Any ideas? A. Any string with an even number must be described by this. Any combination of two letters. Yeah? Is it okay? Odd number. Well, if you know the even number, an odd number of symbols is just A and B followed by an even number of symbols like this. Okay, that was the warming up. Consider the alphabet containing minus, 0, and D represents all these digits. Write a regular expression that represents all integers. For example, 0.43 and minus 0 are not valid integers. You must have an idea about this one. This is not the correct solution. It must start with a digit, and then any combination of 0 and D would do. What's the problem with this? Yeah, I have completely dropped the negative numbers. Okay. Then I insert, it could be minus or it could be the empty string. That means nothing. Is this a correct one? It's almost correct. There is something we're missing.
We have to change the 0 to 1.
To 1?
Yes.
No, then you didn't understand my instructions. 0 is one part. D is 1, 2, 3, 4, 5, 6, 7, up to 9. It represents all the other digits. What about this guy? Does he fit? This one says it must start with it might start with a minus sign, but then it should come 1 to 9, followed by 0 and 1 to 9. So this one doesn't fit. But this is the only one that doesn't fit. So we can safely say that this is a good starting point, and then we are adding this one as our final option. It can be 0 or it can be one of these guys. Yeah? Yeah. I was about to say you're making progress, but that would actually be exaggerating it a bit here, I would say. Yeah, but let's move on. Yeah. If you have been using to solve a task, you have probably seen the plus sign and the question mark as well. Certain patterns are often used, so we have introduced certain shortcuts. R plus means one or more instances of R, but we could just have easily written it using the star like this. Question mark means 0 or 1 instance of R, but we could just as easily have written it like this. But people are using plus and question mark all the time when they are defining regular languages. Rather than saying it can be 1 or 2 or 3 or 4 or 5, we are introducing something called character classes, saying that, well, by this I mean all of them. So one way of writing identifiers in Pascal was to say it starts with one of these followed by one of these. So these constructs are always available in any tool I've seen using regular constructs. And if your regular expression starts to look messy, you should divide them in smaller parts. So for example, you can say that by a letter I mean this one, by a digit I mean this one. Then an identifier in Pascal might be written as a letter followed by any combination of letter and digit. Makes it easier to read. This is what identifiers in Pascal, how they were defined. How are they defined in Java? What additional symbols can be used in Java? are we allowed to use any other things than a letter or a digit? Underscore, and actually one more symbol, seldom used, but you can have a dollar sign also in it. Yeah. Okay, assume now that I defined integers like this. Okay, I'm asking you to implement a program that recognizes integer using according to this definition. How would you do it? You cannot use the available package in Java for it. In general, I give you a regular expression, and I'm asking you to implement something that do the same thing to recognize as a regular expression. People are using something called finite automatas to talk about how to implement them. Let's take a look at this regular expression. It says that it can start with A and B, but after A and B, it must have a B, any number of A's, and followed by a B. You understand this regular expression? This guy, it recognizes the same language. This is the start point. It says it can start with an A or a B. Afterwards, it must have a B. Then any number of A's, and then it must stop with a B. So, for example, must have a look at it. B, B, A, B. Is this a part of this? Will this one recognize this one?
Yes.
Yeah, and you can do it by saying, try to spell it out. B, 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 A, B. You end up in the final state. If you can spell it out, starting from the initial symbol to the final state, then it is okay. If you cannot do it, then it's not okay. Is this one okay? No. You can look at this one, but you can also try this one. A, I have nowhere to go here. It breaks the rule of the finite automata. So for each regular expression, there is a corresponding finite automata. And this is the one that we are implementing to recognize a regular expression. To be a bit more formal, a finite automata, you need to specify 5 things in order to define a finite automata. You have a finite set of states. In my case, it was 0, 1, 2, 3, and 4. You have the input alphabet. These are the labels, available labels on the edges. We have the transition function. A transition function is something that starting in a state, seeing one of the input alphabet, we are moving to another state. This is a function saying that if I'm in state 1 and I see an A, then I should go to state 2. We have one initial state, but we might have many final states. So in this example, I had one initial state and one final state, but there might be more of them. You might have 3 of them. And if you're ending up in one of these, then it's okay, otherwise it's not. Once you have one of these, actually implementation is, implementation is much simpler. Assume that we have a starting point. This is our initial state. We have a set of available final states. This is the next symbol. We are reading it from somewhere, the next symbol in our string. And this is the one saying that if I'm in state this and I see this symbol, I should go to some other state. So the move one here is the one that's saying that if you're in state 2 and you see symbol A, you should go to state 3. This one incorporates the transition function. Then all you have to do is say, okay, I'm starting in the initial state, give me the first character, and then as long as the character is not end of file, move and pick out the next character. Move, pick out the next character. It will do the transition from one step to the other. Once you are done, you are saying, well, am I positioned in the final state? In that case, accepted. Otherwise, we are reacting it. So the trick to implement something that recognizes regular expression is to transform the regular expression to a finite automata and implement that one. It is in many cases trivial. You have been using regular expressions. In what language? C#. Do they have two versions? One where you are compiling it or something like this? If you should do repeated search using the same regular expression, then at least in Java, you can say, okay, take this regular expression and compile it. Then what they are doing is that they are generating this code. They do it once and for all, and then they, if you should only look for something one time, then it's not worth the effort. But if you should do it properly, you should have many strings to check whether they match the pattern or not. Then you should do it this approach. Convert it to a finite automata and implement this one. We have two kinds of automata. We have the ones that we like. They are called deterministic finite automatas, DFA. They are the nice ones. At most one possible transition for each input. Non-deterministic, not DFA. That means if you see a finite automata that looks like this, you are in one state, and when you see an A, you can go two ways. Then you have still a finite automata, but you have this type of guys. This one, is it a NFA or a DFA? It's a DFA. All the outgoing edges from all the nodes have different labels. If you have an NFA, you can be in two states at the same time. It makes the checking more complicated. We started here and we saw an A, then all of a sudden we are in this state and in this state. And then we see a B, then we must take, okay, I'm now in both this state and I see a B, then I move to some other set of states. So in that case, you're working with set of states rather than, so they are more complicated. Yeah. This is an NFA. Now we have one more regular expression here. It says any combination of A and B as long as it ends with ABB. If you take a look at this one and I'm asking you to come up with a finite automata, this would be my first guess. Any combination of A and B, but it must end with ABB. If you look at this one and you look at this one, it looks okay. It says exactly this one. Is it an NFA or a DFA? What? In here and you see an A. Oh, but it is enough that in one transition, we're in state 0 and we see an A, then we can go to both 0 state. We can remain here or we can move over here. It makes it an NFA. Somewhere in the graph we have two outgoing edges that it will split it up and make it non-deterministic. Similar, the same language, but now it is a DFA. Then all of a sudden it's much more complicated. Let's take something that fits this one. Bob fits this one. B, A, B, B. It was too simple. Let's take A, B, B. A, B. A, B, B. It works. Yeah. If you take a look at the regular expression and you should come up with a finite automata, actually coming up with a DFA is often a bit tricky. This one, I said earlier on that this one basically, for me, it looks like this. Start with any combination of A and B, and then we have A, B, B here. Take a look at this one and come up with this one. It's not trivial at all. So in general, constructing an NFA is rather trivial. However, using them, since they are involving all these sets, is much more problematic. A bit of a summary here. There are some theoretical results. For each regular expression, there is a corresponding finite automata. People have proven it that no matter what the regular expression you come up with, there is a corresponding finite automata. They have also shown that for each NFA, there is a corresponding DFA. That means for each regular expression, you can find a DFA in theory, at least. When we are using them, NFAs are much smaller. The memory required is proportional to the length of the regular expression. And the time to do the recognition is proportional to the length of the regular expression and the input string. The problem with DFA is that it might explode. If you have a regular expression, the DFA in the worst case can be 2 to the power of r. It might be extremely complicated. However, once we have a DFA, recognizing them is much faster. It's proportional to the input string that we are checking whether it fits or not. So, conclusion, NFAs are easier to construct given an arbitrary regular expression. DFA simulation is both easier and faster. So the general idea is, if you want to implement this one, is to convert it to an NFA first. Then you can convert the NFA to a DFA, and that's the one you're implementing. There are algorithms. And the simple one is, how do you convert a regular expression to a finite automata, to an NFA? I should. Do you see this one somewhere? Converting an NFA to a DFA is straightforward. You start by putting your regular expression like this. This is the initial state, and this is the final state. Okay, every time you see a concatenation in here, you split them like this. If this is the regular expression, you see concatenation, you split it like this. So in this case, I would say that E, A, B, A star. I have split it like this. And then I take a look at this one. How would you split this one? Yeah, I have it over here as well. You're splitting it like this one. We have still an A here. But we can now say that with B I go to this one, and with A I go to this one as well. And then we have the A star here. And then every time you see a star operator, now I will not be able to do it, but you split it like this. Don't ask me how they come up with this one. There are options to this one. But you are rather than having this one, you insert this combination of epsilon transitions. An epsilon transition means that we are in both states at the same time. So this one says that if we are here, we are also here. And if I see an A, I move over here, but immediately I move back and over here. It's an ugly construct, but by using these rules, you can take any regular expression and you construct an NFA. You are done when all the symbols here are not regular expression, it's just the labels. Follow this rule. This is what goes on inside the one who are generating them automatically. They take the regular expression, they go through these steps, they build an ugly NFA, but it's okay. It's an ugly one, but it will work. So this was my example. A or B star followed by A, B, B. I apply the first rule, concatenation rule, and I divide it like this. This is the starting point. I divide it like this. Then I take a look at this one. No, I take a look at the star here, and I take this part, and I make this part over here. And then I take a look at this one, and I split it like this. It's tedious for a human being to take a more complicated regular expression and go through these steps. It will be an ugly finite automata while, but for a computer it is done in no time. Then we should convert the NFA to a DFA, but this one is tricky and we will drop it. But if you are interested in the next study period, we have a course called 4DV506, compiler construction. It's at an advanced level, but I think you will find it challenging. Then you will have a look at this one and you will also implement them. You will implement your whole compiler actually in this course. So we are dropping it in this course, but for the master students that might be looking at this recording, they will have this one coming up in the next study period. Then we should take a look at how we're converting an NFA to DFA, and we will also implement a small compiler for a subset of Java. So let's move on. How do you convert an FA and finite automata to a regular expression backwards? Now we are just training our brain in some way. Here I have a finite automata, a bit strange notation, but this is the start state, this is the final state, the labels are 0 and 1. We have state 0, 1, 2, and 3. It will recognize certain binary patterns, this one. How would you convert it to a regular expression? You should basically do the backwards of this one. You should try to remove one state at a time. And in the end, you will end up with something that looks like this with your regular expression up here. I will do the first step here to help you understand the idea. Then you can see the slides. Many of these algorithms, if you just see the algorithm, it looks extremely complicated. But once you understand how it works, it's not that complicated. I should try to remove all states but the initial state and the final state. I have Q0 here. Let's just Q0. We have Q1. And was it Q3? Let's remove Q2. 0, 0, How do you remove a state? Well, if we're removing this state, we are missing the opportunity to go from Q3 to Q1, Q0, having seen 1 and 1. So we are removing this one, but we are adding a new edge here, saying that I can go from this one to this one if I see 1 followed by 1. This path is added. If I remove this one, I also remove the possibility to go like this. Yeah. So now we have, you can go from this one to this one by seeing a 1, but you can also do it seeing 1 and 0. We have removed one of them. The next one to remove is this one. Q0, Q3. This was the final state and this is the initial state. So we should remove all but the final and the initial state. You can go from Q0 to Q1 to Q3. You can do it by just seeing 1. Or you can do it by seeing 0, any combination of zeros followed by 0. Yeah? So 0, any combination of zeros and zeros. You can, by removing this one, we are removing the possibility to go like this. So we should add something here saying that now it starts to be a bit more complicated. 1, 1, 0 followed by any number of zeros followed by 0 will take you back here. All right. Okay. What should it be on this one? I cannot go this way. This one only points in this direction. So the only way to go from this one to this one is actually to follow the existing one. Yeah. A closer look at this one says that it looks like Q0, Q3. We have an edge going here. Let's call this one A. We have an edge going in this direction. Let's call this one B. And we have an edge going in this direction. Let's call it C. So A equals to this pattern, B is equal to this pattern, and C is equal to this pattern. But just to remove a bit things. How can I go from initial to final in terms of A, B, and C now? A followed by any combination of any C followed by go back. Can you see it? I would like to go from the initial state to the final state. I can do it by just taking a step. And then any combination of looping here and going back and forth. Any combination of looping here and going back and forth. If you now take this pattern, insert it here. This pattern, insert it here. The first pattern, A, you insert here and here. B, insert here and C here. Then you have your regular expression. So both converting a regular expression to an NFA and converting an NFA, finite automata to a regular expression, it is rather straightforward but tedious. It takes time. In the next assignment, you will be asked to, we will give you some kind of description of something. Like I said, like the one with write the regular expression for integers. We will give something artificial rules. We want you to come up with a finite automata and a regular expression for both of them for each problem we are giving you. You can start with coming up with a regular expression, or you can start with a finite automata. If you have one of them, you can convert between them. Okay, that was a regular expression and finite automatas. Are you familiar with the concept? Why do we need them? They are important, was the answer here from the audience. Yes, everything we tell you is important. Regular expressions you have seen, they are used everywhere. And finite automatas are used everywhere. If you should take a look at the implementation of a game, they are using finite automata. You are moving in your game there. That means you turn around a corner and then you are in the next state. So each scene in a game is a state. And by doing certain manipulations, you move from one state to another state in them. So to describe certain problems, automatas of different kinds are very useful. You are in a certain situation, you do something, you move to a new situation. So both these formalisms are used quite often in programming, and artificial intelligence and things like this. Let's take a break. Let's be back here in 10 minutes. Okay, we talked about regular expressions. If you remember that I started to talk about formal languages. Each regular expression defines a language. And the language is every string recognized by this one. So this regular expression defines a language containing the strings BB, BAB, BAAB, a very long sequence of strings. When we are in programming languages, when we are defining what is an identifier, what is an integer, what is a float, then we are using regular expressions. However, regular expressions are not good enough to define an if statement or something like this. Then we use another tool to define a language called context-free grammars. This context-free grammar defines this language. You should have written it like this using a regular expression. B followed by any number of A's. And this one you should see in as, it says A can be AA or A can be B. And you start with this one, and by applying these two rules, I can apply this rule right away and say, okay, B. I can apply this rule followed by this rule and say A goes to AA, and then I'm replacing this A with a B using this rule. Then I have derived BA. And I can apply this rule any number of times. It will always generate a new lowercase a like this. And then in the end I'm replacing it using this rule. So these are two rules how to rewrite something. The uppercase letters are just help symbols. They are just here to help us. It is the lowercase letters in this case that is the symbols in our language. Did you understand this idea? So these two rules, by using them, I can derive an infinite number of strings. I can define all these strings. I can derive all these strings. I start with this one, and starting from this one, A, I can apply the first rule and say that it goes to A. I can apply the first rule one more time, saying that A goes to A, and then I apply the final rule saying B, A. Uppercase in this lecture will be help symbols, lowercase will be actual symbols of our language. So a context-free grammar contains of rules like this. A simplified notation is to say that A can go to AA or it can go to B. So this one is just a shorter version of these two rules. Think of it as this one is this one or this one. A and B is our alphabet, and uppercase A is a help symbol. If we are talking about the terminology used for context-free symbols, this one are called non-terminals, and these guys are called terminals. But whatever you want. I will probably switch. This is a grammar. B can be parenthesis B, 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 or the empty string. Starting from this one, I can derive the set of all expressions containing balanced parentheses, where we have one left and one right matching each other. I start by, if I would like to show that, for example, this one belongs to this language, I start with B. I apply the rule saying that B can go to BB. I apply the first rule saying that B can go to bracket B. I apply the third rule saying that B can go to the empty string. I apply the first rule saying bracket B. I apply the third rule one more time, saying this. So by applying this rule in certain combinations, I can generate any expression containing parentheses that match each other. And a part of a program language specification might look like this. A list of statements is a list of statements followed by a statement or just a statement. I can apply this any number of rules and generate a sequence of statements using this one. And then I can say that a statement is a while statement, an if statement, or a for statement, and a while statement, and then I can describe them using this one. So context-free grammars are used to describe the syntax of a programming language. It was introduced in the language Algol 1956 or something like this. And ever since then, people have used context-free grammars to describe their programming language. It's the number one representation to describe a syntax of a language. So, a few more exercises for you. Based on the success of my previous exercises, I am not that optimistic in this case. But anyway, write the context-free grammar describing all strings over A, B such that we have an even number of symbols. No? Oops. Oops. It is it is this one. Starting from A here, I can apply any of these rules, and every one of them are generating a new uppercase A, so I can apply them one more time. And every one of them, when I apply one of them, they will generate A, B, B, A, B, B. And then I can stop at any time by applying this one as my final rule. So, A, B, B, A. I start by A. I apply the second rule, A, B, uppercase A. I apply the third rule, making A, B, B, A, A. And then I apply which rule? The empty rule, saying that this one is A, B, B, A. So, in the same way, regular expressions recognized strings matching this pattern. Context-free grammars can be used to derive all valid strings. So, given a context-free grammar, we are defining a language. Write the context-free grammar describing the language. A number of A's followed by the same number of B's. Well, until you get used to it, oops. This one. You start, this is the start symbol. We apply this rule any number of times, and every time we are applying this rule, the number of A's and the number of B's will increase on both sides of uppercase A. And then I close it in the same way as I did it here by applying this one. So, A, B, B. I start with A. I apply the first rule, A, B. I apply the second rule, saying A, B, B, like this. So this one can use to another A here, another B here. Then I will just apply this rule one more time, and it will add another A or another B on this side. Yeah. Could you write down a regular expression for the same language? Well, you're experts at regular expressions, so a last effort here from your side. A regular expression recognizing strings having the same number of A followed by the same number of B's. A finite automata. What would it look like? I have the initial state. I see an A. I go over here. I have initial state and final state in the same node. I see an A. I go here, and I see a B, and I go here. I see an A. I go to the next one. And I see a B, and I go here. Any number of A's followed by the same number of B's will take us back to the final state. If I make this larger, I can take care of it. What is the problem with this one? No matter how large you make this one, I can come up with an example where it will not fit. I just add one more A and one more B. It turns out that this language cannot be described by a regular expression. A regular expression has a certain power, what they can do, but there are many things they cannot do. The context-free grammars are more powerful. They can, everything you can describe with a regular expression, you can describe by a context-free grammar, but not vice versa. So a programming language, which I did here, you want to define your own programming language, you cannot use a regular expression. It is not good enough. It is not detailed enough to contain certain constructs that we are using. So these different definitions, we are saying that the context-free, a regular expression defines a regular language, a context-free grammar defines a context-free language. They are more or less powerful, what you can describe with them. So when you are defining your context-free grammar, you need to specify 4 things. We have the terminals, that was our symbols, lowercase letters. We have the non-terminals. We have the rules. They are called production, is one of them, is called a production. It is a mapping from a non-terminal to a combination of terminals and non-terminals. And we have a well-defined start symbol. This is where we start. A, we can derive something. One of the non-terminals is the start symbol. Another example, arithmetic expressions. A simplified version where we only look at plus and multiplication. That means expressions like this. They can be described by a context-free grammar that looks like this. We have the number of symbols that we are using. That means everything we are using up here in our. We have only one non-terminal E, and E is also the start symbol, and we have a set of rules here. E can go to this one, or it can go to this one, or it can go to this one, or it can go to this one. By taking E as your starting point, you should be able to derive any one of these guys. So if I would like to show that this one is a part of this language, what I should do is I should take my start symbol, I should take a look at these productions, and I would try to derive this string, end up in this one. This is called a derivation. We are proving that a certain expression is a part of this language. So assume that I would like to show that this one is in the language defined by grammar 1. I can start by applying the third rule. Then I have this one. Then I'm applying the first rule. Then I have this one. How should I go on? I would like to this is what I'm aiming at. I should replace E with one of these options. Yeah? Multiplication is it called. Yeah, you should apply multiplication, the fourth rule, and then you should apply 1, replace this one with B and replace this one with C in 2 more rows. So, let's see what we did here is something called the leftmost derivation. Every time I have a number of non-terminals, I always focus on the leftmost of them. So in here I decided, I looked at this one and said, okay, what should I replace this one with in order to reach this one? So every time you have 2 or more non-terminals, you take the leftmost one, then you're doing a leftmost derivation. If you always take the rightmost one, you're doing a rightmost derivation. Once we do a derivation like this, at the same time we are building a tree. This is called the parse tree. It is the internal representation. The first thing that happens when you're compiling your program is that they are reading your program, do a derivation, a very long derivation, and they are building a tree inside the compiler. This is the representation used by a compiler. They don't see the program as you see it, they see it as a tree like this. Anyway, I would like to derive this one from my previous example. I started by applying this rule and then, what did I do here? Okay, I did it in a different order here. Anyway, once you apply a rule like this, you're also building a part of a tree. This is the start symbol. The start symbol will always be the root of your tree. You apply this rule, you add a number of children to it. And then up here we are replacing E with an identifier. It should be C here. In the next step, we are replacing the first one with E plus E. Then we are adding E plus E here. We are then replacing this one with an identifier and later on this one with an identifier. So each step in your derivation add more parts to the tree. So the tree is the result of your derivation when we are talking about how to represent them. Please take forward your pen and paper and try to first do a derivation showing that this one can be derived using this grammar. Students aiming for a somewhat higher grade, they always bring paper and pen. Yeah, a few. So you have your problem. What is it? It's a number of brackets. This is the one that we are aiming for. You start with this one and you should try to derive this string. Where should I start? Should I start with this one? Then we are done. And we haven't reached our goal. Should I start with this one? Why not? Yeah. If I start with this one, I can derive the first part up here, but I will never reach this part. So I must start by splitting it into two expressions. So I'm splitting B into B, B. Then basically we have solved the problem. Then you apply, you should do a leftmost derivation. That means you should focus on the first B. So we are replacing this one with this one, replacing this one with also this one 2 times, and then we are using the empty string. Did you get it? So I do the first part of it. Oh. Like this. Yeah? Straightforward? Good. Come on now. Surprise me here. This is your final effort to today. Yeah. This is your rules. This is what we are aiming at. Do you want to do it on the whiteboard? No. Where do we start? We start by splitting into a multiplication. Very good. That was basically the tricky part. And then when we do a leftmost derivation, we should now focus on this one. Which rule am I supposed to use here? First with the A version. Okay. What do I apply?
Third?
No. We are applying the second rule. A multiplied by, and then we are applying the third rule. E, what was it? Plus E. And then we are applying the first rule 2 times on this one. It's straightforward. You take a look at what you're aiming at. You're aiming at this one. You have your start symbol, and then you combine them in different ways to solve the problem. Then you have shown that this one is a part of the problem. Yeah. I should have done this one. What is the corresponding tree for this derivation? What? For this derivation over here. At the same time as you are doing your derivation, you are constructing the tree from the root down. This is our starting point. We apply this rule. We are splitting it into BB. We were replacing this one with this one. We are setting this one like this. We are replacing this one with an empty string. Then we are looking at this one. We are splitting it into like this, and then it goes on. Yeah. Once you have done your derivation, you can easily construct your tree. Every time you apply a rule, you're adding a new level of children to each node. The parsing problem. I said, how do you, once you have defined your language by using a regular expression, how do you make a program that can recognize whether a string belongs to this regular expression or not? I said you convert it on Automata. This is simple. In a compiler, for example, or if you want to do parsing using a context-free grammar, you should in some way implement this approach. You should, for an input, make a derivation that fits or not fits. If it not fits, then you have an error in your program. We will not go into that. It's the topic for 4 weeks of studies in the compiler course, basically, how to do this. It's complicated, but there are a number of different approaches. Top-down, we have done a top-down approach. We start with a start symbol and we construct the tree top-down. They basically try to implement algorithms doing the same thing as we do. They cannot handle all grammars, but they are very quick. Once you have them up and running, they compile your program very quickly. Another approach is to build your tree bottom-down. Basically, they start with what you're aiming at as the leaves down here. And then they say, okay, these 3 here, they form one of them. And these 3 over here, they form some other non-terminal. They form something B, and then you're building it up to the root, like this. There are 2 different approaches. Both of them are roughly, they work completely different, but they have the same result, basically. Then there are some parsing methods that can handle any context-free grammar. The problem with this one is that they are too slow. They are cubic or worse in time complexity, depending on the input size of the program, and programs are rather large. So it turns out that these algorithms, they are the best in the sense that they can handle every context-free grammar, but they are too slow to be of any practical use. So compilers nowadays are using these 2 approaches. Another problem is that I would like to derive this string. I start with multiplication, and I go on, and I end up there. I could just as well start with addition and do it slightly different, but I can still end up there. I can show that this one is a part of the language in 2 different ways, resulting in 2 different parse trees. This is a problem. We are saying that the grammar is ambiguous. That means you can derive 2 different parse trees from it. If you have a grammar with this property, then the parsing methods that I described earlier, they will not work. So you must avoid having grammars having this property. There are some theoretical results saying, given an ambiguous grammar, does it exist an equivalent unambiguous grammar? Yes. If you have a grammar that you like, it can do all the derivations you're interested in, but you can derive 2 different trees. Then you must take a look at your grammar and rewrite it a bit to avoid this problem. Here I have a new grammar. This is just one grammar with 3 rules this time. I have 3 different non-terminals, E, T, and F, expression, term, and factor, and I have different rules here. And if I would like to derive this expression using this one, I can do it in only one way. the tree will always look like this. So by rewriting the previous grammar into a more complicated grammar, it will always be unambiguous. There is only one tree for every input string. When you get back home and you are feeling bored, I think you should try to show a leftmost derivation using grammar 2 to derive this string. How would you start? E is the start symbol. So. E is your start symbol. That means you have only two rules, E plus T or just T. What? E plus T. E plus T. Yeah, it's the correct choice. Otherwise you will have no chance to get a plus into your expression. And then? Yeah, I can apply E to A, and then I should apply T goes to T multiplied with F. So in a number of steps, I show only the starting point here. You should be able to derive this string, and if you sketch the corresponding tree, it will look something like this. The dangling else problem. This is also, I try to describe what I mean by an if statement. It starts with the keyword if, then we have some kind of an expression, then we have the keyword then we have a statement and an else part. And the else part can be else statement or just empty string. So I'm saying that an if statement looks something like this. Or we can also add this option. This one is optional. Yeah? Do you see that in these grammar rules here? An if statement looks like this followed by an else part, but the else part might just be the empty string, or it's just this. Yeah. This grammar actually allows us two interpretations. If I have this source code, it is exactly the same source code here. I'm just manipulated the indentation. Should the else part belong to the this if or this if? Should it belong like this or should it belong like this? If you write it in Java, which if part would the else belong to? You see the difference between these two? There are different interpretations of them. If you do it in Java, in most programming languages, all of them I am aware of, this is the correct. Else attaches to the closest if statement. But this grammar would allow both these interpretations, and that means it is an ambiguous grammar. You can rewrite this, it looks ugly, but you can get then the correct semantics of your code. I said earlier on that certain expressions, certain languages can be written as context-free, but not with regular expressions, regular languages. There are a number of well-known examples. For example, the matching brackets. You cannot write down a regular expression recognizing matching brackets correctly. And the one that I just showed you, a number of x in this case followed by the same number of y, is also something that you easily can write down with a context-free grammar, but it will not, you cannot come up with a regular expression that it works for. So we are saying that the regular languages are a subset of the context-free languages, or we are saying that context-free grammar is more powerful than regular expressions. You can do more things with a regular expression. But there are certain limitations to context-free languages as well. I would like to recognize all strings of x but there should only be n is a power of 2, which are the first powers of 2 numbers that are power of 2. Yeah. I am only interested in strings having this length. This is a language. It should be x, it should be xx, it should be 4x, 8x, 16x. Yeah, there is not possible to write down a regular, a context-free grammar that will recognize this one. So for certain languages which we easily can express or in some way describe like this, these guys are not good either. We must have something even more powerful to describe them. Yeah. Do you know who Chomsky is? Noam Chomsky. Well, he is an MIT professor in language technology or something like this. He divided all languages into 4 different categories. The easiest ones with the lowest expression power was the regular languages. Then the one that we have been using the last 40 minutes here are the context-free languages. But then he could come up with even more powerful language. And then we have the natural languages. They are rule-based, basically. There are rules for them, but we don't know anything more. There are rules. So he could actually, it is possible to classify every formal language as belonging to one of these categories, 4 categories. If you Google on Noam Chomsky, you will see that he has, well, it was a few years ago, he's probably reaching 5 million hits on Google. It is not because his classification of languages. He is interested in political activities. He writes a lot of articles about American politics. So that's why he's famous. But he's also a clever guy when it comes to computer science. As an example, if I Google myself, I get about 200 hits. So I'm not as clever as Noam Chomsky, I would say. How many hits do you get? If I Google myself, since I've been working at the university for many years, I find myself as a member of some board somewhere. Rather boring reading. Anyway, there are a few things that every guy that studied computer science should know. You should know about Chomsky and his hierarchy of languages. You should know about context-free grammars, regular expression, and finite automata. You cannot call yourself, if you go to Stack Overflow and ask for how to do something and they are saying that it's simple, you design a context-free grammar to do this, then you should say, yes, I understand this. Otherwise, you don't belong here. Any questions? Okay, let's call it a day. We have a lecture tomorrow. I will be in Växjö. This is the final lecture. I will just present an old written exam. Have you seen the old written exams on the Moodle website? Yeah. In the bottom somewhere there are them. Yeah, see you.